Welcome to solverfy.
In here, we have a hydrogen atom which emits a light of wavelength 121.6 nanometers. So the hydrogen atom emits a light of wavelength 121.6 nanometers. Let's evaluate the energy of this photon. So the energy of the photon in this case is clearly equal to hc over lambda. Since this is in nanometers, we'll make use of the fact that hc is equal to 1240 electron volt into nanometer divided by 121.6 nanometers. So this becomes equal to 10.2 electron volts. Now this energy must have come from a certain transition. We make a transition from N2 to a certain N1, where this is the lower quantum number and this is the higher quantum number. The electron makes a transition. It emits a photon of wavelength lambda. So in that case, E2 minus E1 should be equal to the energy of the photon, and we can write E2 minus E1 as negative of 13.6 1 over N2 square minus 1 over N1 square. Now it must be noted that such a high value of the ground state energy, we'll first note this, that the ground state energy is always given as minus 13.6 EVs. Now, it must be noted that such a high value of the photon energy must come from a transition where the gap between N1 and N2 is very large, and such high gaps are only seen for the few initial values, like for N1 is equal to 1, 2, 3, and 4. If I make this more clearly, if this is 1, then the difference between N1 and 2 is very large. Then between 2 and 3 reduces. Between 3 and 4 it reduces even more. Between 4 and 5 it reduces even more, and then it keeps reducing. So let us try to put a value of 2 and 1 for this. If we substitute n2 as equal to 2 and n1 as equal to 1, we see that this calculation exactly becomes 10.2 EVs. So in this case, our initial guess exactly solves the answer. So higher quantum number is 2 and the lower quantum number is 1. And because it makes a transition to n equal to 1, it's a Lyman series. So all the transitions which ultimately land up at n1 equal to 1 are always called Lyman series.